So, Douglas Durian, you've been all over the place with your academic career. You started in Chicago, went to New York at Cornell, you've went to Southern California, UCLA, now at the University of Pennsylvania. Douglas is going to talk to us about AI without a computer.
Going to try?
Yeah.
All right, thank you. So artificial intelligence has, like forever, been the goal of the computer revolution. And well, you know, it's here, obviously, and it's changing our lives in ways we can barely begin to understand. But it's coming at a cost, and that's energy. It takes a tremendous amount of energy to run these systems. And that's sort of under the hood for most people. But it's growing at an exponential rate, and it can't stand. So what I'd like to do is look ahead today and think about a way, if possible, to do AI without a computer, okay? And to do it faster and with a lot less energy. And can it be done? Well, I think so. And the answer is to take advantage of physics. And these little tiny circuits you see before you are actually very small scale prototypes of AI systems that do just that. They train themselves, so they do the training phase and the inference phase autonomously, okay? Well, let's see how that works. So, but first off, so what is a physicist doing in this space, right? Much less a physicist of my background, which actually is in working on particulate systems. Think about grains in a pile of sand and the way they flow when you push on them or tilt it, and have avalanches and things like that. Or bubbles in a foam or droplets in an emulsion. That's my field. So what am I doing here? Well, in fact, this field, this sub-branch of physics that I come from is the same branch of physics that gave us the 2024 Nobel Prizes in Physics, okay? And also the same field that gave us the Nobel Prize in Chemistry this year. And that field is what I would call most broadly statistical physics. It has to do with collections of large numbers of relatively simple objects where the behavior that you're interested in understanding and taking advantage of emerges from the bottom up, okay? So it's something where you requires totally new concepts to understand them. Things that you will not get at within a reductive approach to doing science where you're sort of pulling things apart and going ever deeper into the subatomic structure and the mysteries of quantum mechanics and so forth. Okay, is looking at the behavior that emerges. So in the case of neural networks, you're putting together lots and lots of neurons. Each is individually very simple, but when you put a bunch of them together, magic happens, magic emerges. Okay, so that's the field I come from, statistical physics. And so speaking of the neural network, so to get into it, just remind you how these things work. So they're going to be trained. You're going to train them such that the goal is if you show it, say examples of, I don't know, say images of a dog or a cat, you want to input the data on one side, propagate it through, okay, and you get an answer out the end that tells you what kind of animal it is, or you know, say what's going to be the next word in a sentence, or things like that, okay? And there's lots and lots of parameters involved in this, okay? So AlphaGo, we heard about just a little bit ago, has almost 10 million parameters, okay? 10 million of these little neurons, and to train it, you've got to set the weight of every single neuron. There's a number that you got to figure out, okay, to train it. And you do that by showing it examples. It's supervised. That's the way these things work. AlphaFold 2, which was used for the Nobel Prize to think about protein structure, well, that has nearly 100 million parameters, and ChatGPT has, you know, trillions of parameters. So these are huge systems, statistical physics, okay, statistical. All right, and as I said, they use lots and lots of energy. And so OpenAI, here's some numbers. They used about 25,000 GPUs and about 3 months and $100 million to train it, okay? And they still use vast numbers of GPUs to run the system. The demand for energy is growing exponentially. Here's a plot showing it is basically doubling every couple of years. And it's at such a rate that within maybe 10 years, we would actually double our total energy consumption in this country. Okay, that's a vast amount of energy. How can we do better? Well, let's think about comparing artificial intelligence with biological intelligence. So artificial neural networks versus networks of real neurons like in the brain. And here's an interesting fact. So maybe they have roughly the same number of parameters, okay? But which is more capable and which takes less energy? So artificial neural networks, as magical as they are, can't do as many things as your brain. Your brain can do many, many things at once. It can learn, it can adapt, and it consumes very little energy, okay? It turns out it's about, 20 watts of power, okay? 20 watts of power. So in other words, 1,700 kilojoules per day. Now, with that amount of energy, what could you do with ChatGPT? Well, you could generate 300-word queries. Amazing. The brain is so much more efficient than these artificial neural networks. So what's the magic of the brain? Well, here's a couple things. So first off, so in the brain, learning emerges. Remember I talked about emergent behavior when you put together things that are simple. Learning emerges from the bottom up in the brain, whereas in artificial neural networks, it's more or less imposed from the top down. If you want to think about the neural network as an artificial brain, well, it takes a vastly huger brain to train it and to run it. The brain doesn't have a brain. The brain does it by itself. So this bottom-up learning, this way that it does it in itself, is sort of part of the magic of the brain. Other bits have to do with the way the neurons are connected in artificial neural networks. There's a clear flow of information from left to right, whereas in brain, it's highly interconnected and information is going every which way. So it's highly interconnected. So those are part of the bits. And this gives rise to some interesting features. So for example, the artificial neural networks are highly optimized and they're pretty fragile, whereas the brain is extremely robust to damage. You can damage your brain quite extensively. It can still work at a very, very high level. So interesting things other than energy conservation could emerge if we could sort of capture some of this brain-like magic. Okay, so where is the energy being spent in a computer? Well, a lot of it has to do with the so-called von Neumann architecture and the resulting bottleneck. So by contrast with brains, in brains, the computation and the memory are all intertwined. They're all there together. But in computers, they're in separate locations. There's a processing unit, there's a memory unit, and you have to shuffle data back and forth between those two things continually. And that is a source of limiting speed and a source of vast energy consumption. And things like GPUs, they try to put those things close together and save energy that way. But the von Neumann bottleneck is there. So can we get around it? Can we do things in memory like in a brain? So that's where we're going to try to go. Other people have thought about this. So actually there's a field called neuromorphic computing, which has many, many flavors, but one of which, maybe the purest, is to actually try to build artificial neurons, build circuitry that mimics the action of biological neurons. So spiking neural networks. So this is the thing. It's been done for like 30 years, and here's some example. So it can do the training phase, it can do the inference phase, all in memory with these spiking neural nets. Well, after about 30 years of research and work on this, the largest that can be made is still only a few thousand neurons. So these are difficult, they're complicated, they probably can't be scaled up much further. There are applications to be sure, but these are not going to disrupt our current way of doing AI. No way. How about other physical systems where the memory is used, well, where the compute is done in memory. There's lots of things going on in this space, actually. So for example, on the left, we see a crossbar array of memristive elements. And you can write in the resistance of those things, and you can do these things, use these things to do matrix multiplication operations, which are at the heart of AI. In the middle, there's a system. This is a system of little micromechanical resonators that can do speech recognition. On the right is a series of actually lots of different little devices where you feed in the data as a stream, and you can train these things. So these are all really cool. They do the computation physically in memory, but they're all trained externally. All the training is done outside in a computer, and the weights, if you like to call them that, the parameters, the adjustment of the parameters is done externally on a computer model of your system, and the results are fed back in. Okay? So these are also therefore energy consumptive in the training phase, and they're also difficult to scale up for lots of reasons, including the fact that your model is never going to be a perfect model of the actual physical system. What can we do?
Well,
oh, question, good.
That last point is exactly right. If the data is static, you can do this. If the data is dynamic, it's much more difficult, right?
Yeah. So,
sorry, just quickly on the set of examples of other ways to do this kind of in-memory computing, are you basically asserting that none of these are going to bear fruit?
None of these are going to be what?
Ever bear fruit?
Oh, they are going to bear fruit, but they're never going to displace our large language models of today.
Okay.
I don't think you can possibly scale them up to the right sizes. I think that it's going to be small scale applications. All right, so in my lab, here's a couple examples of the networks that we're working with. One is just on the top. The one I'll focus on today is a network of resistors where the resistances or the conductance of the edges are the learning parameters that we'll adjust. And so that's where we're going to go. And so here's the idea. Okay, so picture a network. It's highly interconnected. It's highly recurrent, if you will. The idea is to impose the data, say as voltages, on designated input nodes, and read the answer as the voltages that appear on designated output nodes, and to adjust the conductances to get there, to do what you want. Okay? So the physical computation is nice. So if you remember back to your physics, the way you could solve this kind of problem in the electrical cases with Kirchhoff's laws and Ohm's law. And physically, the principle at heart, though, that we're going to take advantage of, is that the currents spring up in such a way that the total power consumption is minimized. The currents spring up in such a way as to minimize energy consumption. Okay? So that's a physics principle we're going to take advantage of. And as I said, the goal is to adjust the conductances so that the outputs are a desired function of the inputs. That's our AI. And how are we going to do that? It seems like a hard problem because it's a huge network. And, you know, you've got a lot of things to solve there. It's very highly interconnected. Well, we're going to actually take advantage of this fact that physics minimizes power consumption in the current springing up. So let me tell you how that works. It's a scheme that we call coupled learning, and it's an example of a contrastive local learning scheme. Okay? So how are we going to do that? So we're going to contrast the behavior of the network under two sets of conditions, operating conditions or boundary conditions, if you will. One is we're going to call it the free condition. We're going to just read the outputs. So impose the inputs and read the outputs. Let the output nodes do what they want to do. But if it's not trained, the output voltages are at the wrong value. So what we're going to do is, it's our second boundary condition, we're going to clamp the output nodes to the right values. We're going to impose the training data as voltages on the output nodes. That's where we do the supervised learning part. And because the output nodes are no longer doing what they want to do to minimize power, Of course, when you clamp those voltages, you increase the energy consumption. So the clamp condition takes more power to run than the free condition. And that's something we're going to take advantage of. And the scheme, as I said, is called coupled learning, and it was invented by a postdoc at Penn, Naki Stern, and his advisor and my wife, Andrea Liu. Okay, so how does it work? Warning, sorry. I'm going to show you some equations. Professor's got a professor, okay? Sorry. So here's the way we do it. So ordinarily what you would do is, like, if you're going to fit a function, you just minimize chi squared, okay? Take the desired minus the actual, square it, do gradient descent, drive it to 0 by adjusting your parameters. Then you will have learned. And we've got lots of ways of doing that. Okay? We, on the other hand, can work now with a physical contrast function that's the difference in powers between the clamped and the free cases. This is intrinsically a positive quantity. So I can drive this to 0 with gradient descent. If I use gradient descent, it won't take it to minus infinity. It'll take it just to 0 and stop. Okay, so here's the math. So Kj is the conductance of edge j. Its time derivative, Kj dot, is going to be proportional to minus the derivative with respect to Kj of the contrast function, the power difference in those two different boundary conditions. Now, those two powers are both global quantities, just sum over all the edges of v squared over r. That's the freshman physics thing. And since I didn't square it, I can run that derivative through, and that's what I get. And this is a local learning rule. And now that I'm thinking about it, I didn't make a big enough fuss about local versus global in the context of brain versus artificial neural networks. So the brain, the learning rule is Hebbian. Neurons that fire together wire together. Each neuron does its updates based on conditions it feels. It doesn't know about all the other neurons in the brain. Whereas in artificial neural networks, to update things in one layer, you need to know, to update this neuron in the artificial, you need to know about the weights of all the neurons in that layer. It requires global information. This requires only local information, like the Hebbian rule. I can update edge j just by knowing the voltage drop across it under two different boundary conditions. And that's super cool. That means I don't need to know what everything is doing in the network. I can do it all locally. And the miracle is that this local rule then optimizes a global optimization problem. So this is cool. So we anticipate some advantages. We anticipate that it operates more like the brain in lots of ways. Computation is done physically. It's done locally, in memory. So, you know, it ought to be more like a brain, and hopefully that these will give us some advantages, like making it fast and energy efficient, and also robust to damage. So let's see how it can go. So first off, is the scheme total nonsense or not? No, it's not total nonsense. Naki simulated it. So here's an example. So we trained this particular network to classify handwritten digits, okay? And you could do that with good accuracy, okay? And it's not actually, however, a good computation scheme. You wouldn't want to throw away your artificial neural networks and do it this way. This requires a lot of computer power. This is not taking advantage of the local learning rule. A computer had to do it all, okay? And I want to get rid of computers. So the coupled learning rule is not a good computation scheme with a computer. It's good for doing things physically. So we got to do this not in silico, but in laboratorium. How are we going to do that? Well, it's easy enough to get your hands on variable resistors, for example, and you just give them a little voltage pulse to a given pin, and it can click up or down the resistance. That's easy. But we still got a problem, because the learning rule is local in space, but not in time. You got to apply two different boundary conditions. What are you going to do? Run free, go in there and measure the voltage drop, write it down, apply the clamp boundary conditions, go in there, measure it, write it down, compare them, and feed the answer back in for the update, that would be kind of silly. That would be defeating the purpose. I don't want to instrument this up. I want to take advantage of the local learning rules, so we need a trick. And here it is. We're actually going to build digital twins of each other. So we're going to build two identical networks, as identical as we can make them. One is going to be dedicated to running the free. One is going to be dedicated to running the clamped. They live right on top of each other. Okay? So we can easily then build some circuitry that will compare the voltage drops across the identical twin edges under the two conditions and see if the resistance should go up or down. So that's our twin network trick. And this is built by my postdoc, Sam Dillevu, who's absolutely fantastic. And this is our very first contrastive local learning network. Not very big, is it? 16 identically constructed edges. He wired these up on little breadboards by hand. And what can it do? Well, it's small, so it can't do much. But here's one example. It can do classifications, not of images, okay? So this so-called iris data set is just a set of 4 measurements for each flower. So measure the length and the widths of the petal and the sepal for a bunch of flowers, okay? And in this case, there's 3 species, and there's 50 flowers from each species. We're going to break that up into a test set and a training set and a test set and go to town. So our network is big enough for this. We've got enough nodes to handle that. So for each of the 4 measurements, we're going to translate those to a voltage and apply it to a designated input node. We're going to reserve 1 node for ground. And since we have 3 species of flower, there's going to be 3 output nodes. And behold, after a few epochs, after a few times cycling through the training data set, it can classify it to better than 95%. And these are linear resistors. This is about as good as you can do with this particular data set with a linear classifier. So we're very happy with this. It trained itself. All we did is show it the data. No computer involved. All right. How about other features? Well, as I said, computers are fragile. You can't damage a computer physically very much and expect it to work, but the brain, on the other hand, not so. Here's a hemispherectomy image, okay? In severe, extreme cases, this is a procedure, and this person can still operate at a very, very high level, even though they're missing half their brain. So our networks actually fall in that same spectrum. Okay? They're closer to the brains in this sense than artificial neural networks. We can snip edges, we can break edges, and it can still retrain. Heck, Sam had to hunt for edges that make a difference. Usually if he clips an edge, nothing happens. They're very robust to damage. Okay? And this means, I think, and I hope, that they're going to be manufacturable at scale because of this feature. Okay? There can be imperfections, and we don't care. It can still learn. Therefore, we can make it large. All right. We also need to make it nonlinear. You may know nonlinearity is part of the secret sauce of artificial neural networks. We have to have nonlinearities. Our linear systems won't cut it. And transistors can do that. They've got a weird nonlinearity, but that's okay. So here's an example of our second generation made with transistors. It's got the feature that is both nonlinear and it's more directly micro-manufacturable. You could take our designs now and really put them on a chip. So that's a cool thing. And it's a little bit larger than before, but not much. Okay, there's still only 30 edges. And here's an example of what it can do. So here's binary classification. So what we've got are training data set composed of the dots you see there. There's 2 colors, right? And the idea is to figure out, given input 1, the values of input 1 and input 2, whether you're blue or whether you're orange. So the dots, that's the ground truth. And the background color is actually the test set. And you see here at time 0, it's not trained very well. In the upper right, yeah, it's blue, but in the lower left, it should be orange and it's still blue. The decision boundary is this black smear that's down along the bottom. So above the black smear, it thinks it's blue, and below it, it thinks it's orange. And let's run it. So there it is with time. It moves up, it bends over, it curves, so it's nonlinear. It's taking advantage of the nonlinearity. And lo and behold, it does a good job separating or classifying those two different colors. So there we go, binary classification. So next up, we got to move to larger scales. Sam has been an absolute hero building these things on breadboards. He's both proud and ashamed. I think he should be more proud than ashamed. People who make so many breadboards, right? So we're putting these on printed circuit boards now, and we also have a new kind of a new circuit. Also takes advantage of transistors, but with a different circuitry that Mark designed, and that's coming along too. So we're making a progression to larger scales, and we're having a lot of fun with this. And I think you can see the dream then is to see how far we can run with this as a new hardware platform for doing AI. It's both fast and energy efficient. So here's some numbers to keep in mind. These are the things that we want to shoot for. Okay, so state-of-the-art large language models have 10 to 12 parameters. And in terms of energy consumption, well, 10 to the minus 12 joules per parameter per inference. Okay, so there's the number. There's the thing we'd try to go for. Generation 2 on breadboards, we've only got 30 parameters. Okay, so we got a long ways to go, duh. But look at this. Already in these breadboards, these dumb breadboards, we're consuming, they're not optimized at all, 10 to the minus 11 joules per parameter per inference. So they're pretty darn good already. And the chips that we've got now, actually, they're 100 times better than the state of the art with no optimization we've done whatsoever. We think if we optimize this with a state-of-the-art fabrication process, and if it scales up, that's a big if, of course, if it scales up, then we think we should, with this current design already, be able to put 10 to the 9th edges on one chip. Okay, so if we want to get to 10 to the 12th, it would just require 1,000 chips. That should be easy. And the energy consumption, we think, is going to be a million-fold better. Okay, so that's the dream. So are we going to get there? Are we going to disrupt the current paradigm? Who knows? Are we going to find niche applications along the way? Better. I think there's kind of precedent for this already. But in systems that that don't train themselves, our systems will train themselves.
You sort of had a little throwaway line there, in which you said, are we going to disrupt? Clearly you think you're going to. At least that's how I'm reading your tone. Am I wrong? Is this a NVIDIA killer?
I mean, come ask me in 10 years. We're a long ways off. So I think the way it's going to go is we have to scale this up. And I showed you a little bit about the progression. We're going to go up by factors of 3, factors of 10 every time. And I'll bet you anything. I mean, this is how research goes. Every time you go up by a factor of 10, you're going to encounter new problems. And we're going to see how far we can go. Okay? So I don't know. I've got hope because this thing is robust to damage and because it's learning. The learning emerges in spite of imperfections. I didn't emphasize this also, but if you think about the circuitry in your brain by comparison with circuitry in computers, oh my God, it's night and day. Circuitry in your brain is slow, and it's noisy and mistake prone. You never know when those neurons are going to fire. It's not reliable at all. It's remarkably, remarkably slow and noisy. Yet it works miraculously. So we hope that our system will have some of that magic that will let us scale it up. Will it? Let's see.
Could you?
So, listening to this, I had two questions. The first was just about quantity of parameters and kind of sizing. You answered that when you showed the Gen 3 chip. But the second one is you mentioned that brain processing is slow because you are running two systems in parallel. Now, admittedly, you've moved to chips, but is there a difference in speed between kind of the current way we're doing things with these GPUs and with, I'm sorry, I've forgotten the catchy term you used to call this, brain-like computing?
Yeah. Well, the speed of our circuitry is very, very fast. So how long does it take to equilibrate? Well, basically, the rate limiting step for us is how long it takes for us to apply the input data. As soon as we apply the input data, the currents spring up. There's an RC time, but the residual capacitance is small. It's nearly instantaneous. So the physical computation is super, super, super fast. We're every bit as faster than state of the art, okay? For sure. The rate limiting step is showing it the data and reading the outputs.
You talked about this architecture being resilient and gave some examples where snipping edges demonstrated some resiliency. How far did you push the measurement of resiliency in terms of what's the decay function look like? How much damage can you do before it becomes inoperable or something like that? Have you plotted a curve on that, or you have some theory around that?
These are great questions. And experimentally, we don't have a lot to show because our systems are kind of small. Theoretically, my theory colleagues have done a little more work on this. And the thing to know is that typically you want to operate in the over-parameterized regime. You want to have many more parameters than constraints. So that means lots and lots of sort of extra elements. So if one screws up, it can sort of learn by having information flow through different paths. So in our case, that would mean as long as you've got lots and lots of a lot more edges than input and output nodes. Okay, so that's a rough rule of thumb. Many more edges than input and output nodes.
Question here.
Hey.
Do you have information theory people in your group? Because there's a lot of analogies here with like Hamming codes and like par file encodings, lossless encoding kind of problems.
We don't.
It feels like you should email those people.
I agree. We've thought about this a little bit.
Yeah, I mean, I think this is really interesting because I'm immediately like, well, how many parameters do you need? What is the redundancy factor? What, you know, there's a lot of theory out there for you.
Yeah, for sure. And this is partly why we're having so much fun with this. It's like we have to think through everything from the ground up because it's a different way of doing the computation. So it's going to be a lot of fun.
Right, but the information theory isn't predicated on the physical instantiation of the model, right? It's like mathematical.
Yeah. Okay, so just in summary, can you do it? How to do AI with a computer? Without a computer, you take advantage of physics, and two ways, okay? And both to do the physical computation and to do the learning, both physically by a process. Basically, it's just letting a physical system relax in response to a stimulus. That's physics. And we think we can save time, and we think we can save energy. And let me just stop right there and thank all of my collaborators on this project.
Thank you, Douglas. So I always like to know, how did you get the idea to pursue this? What was the inspiration?
It's a great question. So so it came about through Andrea, through my wife and colleague. Okay, so she's been working on mechanical models of proteins. Remember the Nobel Prize in Chemistry using AI, AlphaFold? Well, so she's been working on mechanical networks, and her idea was to try to figure out ways to do, for example, allostery. So if, one of the functions of the protein is if an enzyme docks here, if that's the right word, I'm not a biochemist, it's going to deform the molecule here, and you want some prescribed action at a distance to open up or close to allow the docking of another molecule to catalyze some biochemical reaction. So it's training a large-scale network to do an input-output response function that's very complex. So it's thinking about doing that inverse problem physically rather than yeah.
So how far back does that inspiration go to where you are today?
Yeah, that line of research goes back actually a couple decades, and it touches on my particular field, which is granular systems, which are actually mechanical spring networks in weird ways. So if you think about a pile of sand, if the grains are not moving, they're pushing into each other, or bubbles in a foam, they're pushing on each other. You can model those interactions by springs. So a lot of forms of particulate matter are actually spring networks. And spring networks are like resistor networks, except a little more complicated because they involve force vectors rather than voltage and current scalars. So for me, this goes back to the beginning of my career.
Okay.
Actually.
Cool. All right. Mercedes.
Hey.
This is a bit of a side question, but your partner is also a collaborator.
Yes.
Do you set boundaries at home?
Rarely. Yeah. No, our biggest fights are not about our kids or finances. It's about science. We've got different ideas. So our biggest fights are about science. Yeah, but
Right.
but she's a theorist and I'm an experimentalist, so I always get the last word.
So you say.
Yeah.
All right. Douglas, thank you so much.
Thank you.
Fascinating.